In this video, we're going to talk about phase diagram. The learning competency for this video is to interpret the phase diagram of water and carbon dioxide. And here are the specific learning outcomes. A phase is just another term for solid, liquid, or gas, right? Plus diagram, which is a picture. So a phase diagram is like a map. So it tells us which state or states of matter exist for a given set of temperature and pressure conditions. So speaking of temperature, what is a temperature? Temperature is one of the fundamental quantities in science, which is the average kinetic energy of particles measured in Celsius, Kelvin, or Fahrenheit. So if you have high temperature, the molecules move fast, right? So there is higher kinetic energy. Now, if you have low temperature, the molecules move slowly. We also mentioned pressure. Pressure is a measure of how tightly matter is squeezed together in units of atmospheres, bars, torrs, pascals, or even pounds per inches squared, or PSI, right? Now, in relation to our previous video, we have here the two allotropes of carbon. So, the question which one is stable depends on both temperature and pressure. So, what exactly is a phase diagram? This figure shows a simple phase diagram. You will see three lines and three areas. It's the solid, liquid, and vapor. And you will also see 2 points marked as C and D. So a phase diagram is a graphical representation of the physical states of a substance under different conditions of temperature and pressure. So it gives the possible combinations of pressure and temperature at which certain physical state or states a substance would be observed. So basically, it summarizes the conditions at which a substance exists as a solid, liquid, or gas. So you have to remember that each substance has its own phase diagram. So let's discuss the features of a phase diagram. Phase diagrams are plots of pressure and temperature. Okay, so pressure is usually in atmosphere, so this is the unit conversion, and temperature is usually in Kelvin. Okay, but some references they use degree Celsius. Okay, for example, you have a pure substance at three different sets of conditions of temperature and pressure corresponding to 1, 2, 3 as seen in this graph. So at area 1, your substance will be solid. Okay, at area 2, it will be liquid. At area 3, it will be vapor, okay, or gas. Now, what's the difference between gas and vapor? So, vapor is a mixture of two or more different phases at room temperature. So, these phases are liquid and gaseous phase. Gases usually contains a single thermodynamic state at room temperature. But in this sense, we can use it alternately. For example, you have a solid here and you increase the temperature at constant pressure. Okay, so at some point, your solid will cross this line. So when that happens, the solid becomes liquid because it's in the liquid area because it crosses the solid liquid equilibrium. So some books they call it the melting or freezing curve. It's the blue one. Okay. So at what point did the solid start to melt? It's here. So we call this the melting temperature. Okay. Now, if you repeated this at higher fixed pressure, let's say this one, the melting temperature would be higher because the line between the solid and liquid areas sloped slightly forward. So if we're going to look at this, you increase the temperature and you plot it. So this will be your new melting temperature. This transition simply shows the effect of pressure on melting point. So anywhere on this line, on this blue line, there is an equilibrium between solid and liquid. Okay, so you can apply here the Le Chatelier's principle. So apply it just as if it was a chemical equilibrium. Le Chatelier's principle is also known as the equilibrium law, remember? So it states that when a system experiences a disturbance, such as a change in concentration, temperature, or pressure, it will respond to restore a new equilibrium state. Okay, so we're not going to discuss it further, but you can apply it here. So if you increase the pressure, the equilibrium will move in such a way to counter the change you just have made. So why does this slope leans forward? So remember that for most substances, the solids occupy smaller volume than liquids. So this is the same as before, but now you're converting from liquid to solid. To make it easier to visualize, let's say you have a lot of substances. Okay? If you have a lot of substances at constant temperature and various pressure, and you align it to the solid liquid equilibrium line, you will see that you have freezing points different from the original. Okay, so from this one with the green line. So as you decrease the pressure, the melting point decreases. So why will it decrease? Because the solid takes up slightly less space for most substances. That means that increasing the pressure on the equilibrium mixture of solid and liquid will convert the mixture back into the solid again. So we say that pressure is directly proportional to the melting or freezing point. Okay, you can see this effect here. This sample is liquid because it's in the liquid area, right? Now, I decided to increase the pressure up to here. So at this point, my substance is solid. So I can make this liquid again by decreasing the pressure. Okay, so it will hit the same point. Now, you can also use temperature. So to make it liquid again at this high pressure, or to make it melt at this higher pressure, you need to increase its temperature. Okay, this will give you now the new melting temperature. So that is why the melting point line slopes forward for most substances. Okay, so you have to remember this. Now, the extra heat needed to further melt the solid here is what we call the heat of fusion. Okay, so that would be for your other topics. Now, in theory, the melting point of a solid should be equal or should be the same as the freezing point of the liquid. However, in practice, in real life scenarios, small differences between these quantities can be observed. It may be it may be due to a lot of things. For example, impurities. So we can also move liquid to vapor. Okay, so you can do this by changing the temperature or the pressure, right? So this liquid will turn to vapor when it boils, meaning when it crosses the liquid vapor equilibrium line. So how will you do it? First, by increasing the temperature at constant pressure. Okay, so you will have this boiling point. Again, what is the significance of this line separating the two areas? It means that anywhere along this line, there will be an equilibrium between the liquid and the vapor. Okay, so this line is most easily seen as the effect of pressure on the boiling point of the liquid. So let's say you decrease the pressure, you will have the sample here, giving you the new boiling temperature. Now, if you notice, as the pressure decreases, the boiling point decreases. So we can say that the pressure is directly proportional to the boiling point. So again, we call this the liquid vapor equilibrium line. Okay, so some references they call it the vaporization curve or the condensation curve. So this line or curve represents the transition between gaseous and liquid states. Vaporization because the liquid becomes gas. Condensation because the gas becomes liquid. Okay? Now, if you notice, you have this letter C here. This is known as the critical point, and the temperature and pressure corresponding to this are known as the critical temperature and the critical pressure. Now, if you have a gas sample at lower temperature, lower than the critical point, for example, here, and you increase the pressure, you will eventually cross the liquid vapor equilibrium and the vapor will condense to give a liquid, right? So this works fine as long as the gas is below the critical temperature. What though if your temperature was above the critical temperature? Let's say here, okay? Then there wouldn't be any line to cross. That is because above the critical temperature, it is impossible to condense a gas into liquid just by increasing the pressure. So all you get is a highly compressed gas. So this compressed gas is what we call a supercritical fluid. And this one is what we call the supercritical fluid region. Supercritical fluids are any substances at a temperature and pressure above its critical point, where distinct liquids and gas phases do not exist. Okay, sir, I thought it's gas. Why is it fluid? Basically, supercritical fluids have properties between those of a gas and a liquid. So a supercritical fluid can effuse through solids like a gas and dissolve materials like a liquid. So just think of it this way. At temperatures above the critical temperature, the kinetic energy of the molecules is high enough to overcome any intermolecular forces that would condense the sample into the liquid phase. So it will be just gas. But since the pressure is so high, so above the critical pressure, it would not allow any sample to stay in pure gaseous state. Therefore, a balance between these two tendencies is achieved and the substance exists in a state between a gas and a liquid. So the critical temperature obviously varies from substance to substance. And, of course, depends on the strength of the attractions between the particles. Okay, so just to relate our discussion from the previous video, the stronger the IMF, the higher the critical temperature. Okay, now there is another line here, this one. Okay, this represents the solid vapor equilibrium. So it is commonly known as sublimation curve or deposition curve. It is the curve on a phase diagram which represents the transition between gaseous and solid states. Now, if the conditions of temperature and pressure fell exactly on this line, you can change directly from solid to vapor or vice versa without going through the liquid phase. Okay? So once again, you can cross the line by either increasing the temperature of the solid or decreasing the pressure. So the pressure obviously has to be low enough that a liquid cannot form. So in other words, it has to happen below the point labeled as T. Okay? So this is called as the triple point. So at the triple point, the three lines meet. So you have here the solid liquid equilibrium, liquid vapor equilibrium, and the solid vapor equilibrium. In real life, it looks like this. Observe how the sample change its form three times. Another visual is this one. So the water here is at triple point. So here it's constantly melting, freezing, and boiling at the same time. Now, this summarizes the phase diagram that we have studied. So here is the triple point, the critical point, and the lines. Okay? Now, what is this broken line? Before we talk about this line, let's recall the normal melting and boiling point. Okay, so the normal melting and boiling points are those when the pressure is at 1 atmosphere. So what you have to do is just write a straight line extending from the 1 atmosphere mark. So now, what does a phase diagram of water look like? So it looks like this, okay? And this is the broken line that I have showed you a while ago. So there is only one difference between this and the usual phase diagram, okay? If you notice, it's this one, okay? So the solid liquid equilibrium line or the melting point line slopes backwards rather than forwards. Okay, so remember in the usual phase diagram, melting point increases as pressure increases. But here in water, the melting point gets lower at higher pressures. Now, of course, the question is why? So this is because ice is less dense than liquid water, which is caused by the crystal structure of the solid phase. So remember in our previous discussion, in the solid forms of water and some other substances, the molecules crystallize in a lattice with greater average space between molecules, thus resulting in a solid occupying a larger volume and consequently with a lower density than the liquid. So when it melts, the liquid water formed occupies a smaller volume. Okay? So suppose you have this equilibrium. So ice is less dense than water. So when it melts, the water formed occupies a smaller volume. And if you increase the pressure on it, according to the Le Chatelier's principle, the equilibrium will move to reduce the pressure again. That means that it will move to the side with the smaller volume. So liquid water is produced. Okay, so for example, this one. So to make the liquid water freeze again at this higher pressure, you will have to reduce the temperature. So higher pressure means lower freezing or melting points. So in water, the melting point and the pressure has an indirect or inverse relationship. Okay, so notice that the triple point for water occurs at a very low pressure. This one, it's just 0.006 atmospheres below the normal atmosphere, which is 1, and at 273.15 Kelvin. Okay, also notice that the critical temperature is 647 Kelvin, which means that it would be impossible to convert water from a gas to a liquid by compressing it above this temperature. Now, the critical pressure of a substance is the pressure required to liquefy a gas at its critical temperature, and this water has 218 atmosphere. Now, how does the phase diagram for carbon dioxide look like? So the figure shows the phase diagram of carbon dioxide or CO2. Now, the only special thing about this phase diagram is the position of the triple point. They are here. This is the normal phase diagram, and this is the phase diagram for water. So again, the only thing special about the phase diagram of CO2 is the position of the triple point, which is well above atmospheric pressure. So meaning it is impossible to get any liquid carbon dioxide at pressures less than 5.2 atmospheres. Okay? So that means at 1 atmosphere pressure, carbon dioxide will sublime at temperatures of 78 degrees Celsius or 195.15 Kelvin. This is the reason why solid carbon dioxide is often known as dry ice. It's because you can't get liquid carbon dioxide under normal conditions. Only the solid or the vapor phase.